Welcome to today's Explainer. We are jumping right in today to look at one of the most incredibly engineered systems in the human body, the kidney. You can really think of it as the ultimate biological filtration plant. Every single day, your body goes through all these complex metabolic processes that generate waste. And honestly, if that waste builds up, it's a massive problem. Your kidneys are the master regulators working behind the scenes to solve this. They're meticulously filtering your blood, balancing your internal chemistry, and basically tossing out the trash while keeping exactly what you need to survive. It's an absolute marvel of fluid dynamics, and today we're going to understand exactly how it works.
Here's our game plan. First, we'll meet the glomerular filter. Then, look at the physical forces driving the filtration rate and tackle the concept of clearance. After that, we'll explore how different substances are handled, and finally, we'll connect the whole thing to eGFR and your real-world kidney health.
Section 1. Meet the glomerular filter. Okay, let's dive right into this and zoom way down to the microscopic level to look at the functional unit where the actual magic of blood filtration happens.
Before we look at the structure itself, we really need to define our most critical metric here, the glomerular filtration rate, or GFR. Simply put, your GFR is how much filtrate is physically removed from the blood every single minute. Now, I want to emphasize an absolutely crucial distinction here. GFR is not, I repeat, not the total volume of blood flowing through the system. Instead, it's specifically the volume of the purified protein-free fluid, the filtrate, that gets squeezed out of the blood and into the kidney's plumbing.
As you'll see here, this is our main processing unit, the glomerulus. It acts just like a super sophisticated biological sieve. Notice how the unfiltered blood rushes in through this vessel right here, called the afferent arteriole. As it weaves through that dense clump of tiny, porous capillaries, a portion of the fluid is pushed out. That right there is your glomerular filtrate. The remaining, somewhat thicker and more concentrated blood then exits through the efferent arteriole.
And this table brilliantly illustrates that sieve metaphor in action. Look at how the glomerular membrane discriminates almost entirely based on molecular size. Tiny metabolic waste products like urea, with a mass of 60 Daltons, which is just a tiny unit of molecular weight, have a filtrate to plasma ratio of 1.0. That means they pass freely right through the filter, no problem. The same goes for small essential molecules like glucose. But check out albumin down at the bottom. It's a massive plasma protein weighing 69,000 Daltons, and its ratio is less than 0.01, so it is completely blocked by a healthy filter. This is exactly why routine tests on hospital wards check your urine for protein, because if massive proteins like albumin are showing up in the urine, it means the physical filter is broken.
Section 2. Driving the filtration rate. All right, so we know what the physical filter looks like, but what are the invisible physical forces that actually push the fluid across that barrier in the first place?
Well, the whole system operates on this incredibly precise physical balancing act governed by what we call Starling forces. It's essentially a microscopic tug-of-war of pressures. Favoring filtration, you have the heavy hitter, the hydrostatic blood pressure inside the glomerular capillaries pushing fluid outward with a force of about 60 millimeters of mercury. But fighting against that, totally opposing the filtration, you've got two counterforces. First, the physical pressure of the fluid that's already sitting in Bowman space pushing back with 15 millimeters of mercury. Second, the osmotic pull of those big plasma proteins we just talked about. They desperately want to hold on to water, pulling back with a force of 29 millimeters of mercury. So you have 60 pushing out and 44 pushing back in. That net difference, that is exactly what drives your GFR.
If you follow the red line on this graph, you can literally trace that pressure journey. The blood pressure drops as it moves through the renal vessels. In the glomerulus, that orange shaded area represents the net outward filtration we just calculated. But watch what happens as the blood continues on into the peritubular capillaries. The pressure drops so much that the Starling force balance actually reverses. See the blue shaded area? It shows how the system suddenly favors absorption, allowing the blood to reclaim vital fluids and nutrients later down the line. I mean, what an exquisitely designed, self-balancing system.
Section 3. The concept of clearance. Now that we've got a handle on the physics, how do we actually measure the efficiency of this biological plant? For that, we use a concept called renal clearance.
So, renal clearance is defined as the volume of plasma that is completely cleared of a substance by the kidney per unit of time, usually expressed in milliliters per minute. Now, a very common mistake here, actually, scratch that, it's more of a major misconception, is thinking that clearance refers to the amount of the substance itself, like the actual grams of sodium or milligrams of urea. It doesn't. Clearance is specifically tracking the volume of the plasma that has been swept completely clean.
And here is the math behind it. Don't let it intimidate you, it's actually super logical. CS stands for the clearance of the substance. UU is the concentration of that substance in your urine.
V is your urine flow rate, and PS is the concentration of that substance in your blood plasma. So the crucial point is, the calculation is just what's ending up in the urine, multiplied by how fast the urine is flowing, all divided by what was originally in the blood. This simple equation is a real game changer because it lets us mathematically peer inside the kidney to see exactly how well it's working.
Section 4, substance handling. But here's the thing. Not everything that enters the kidney has the same fate. Once plasma is filtered, the kidney actively manages different molecules in totally different ways.
We can broadly categorize this into 4 different types of molecular handling. Substance A, like creatinine, goes through filtration only. What goes through the filter goes straight to the toilet. The body doesn't try to save it or add to it. Substance B represents things like electrolytes or ions. These get filtered, but then the body partially reabsorbs them based on exactly what it needs to stay balanced that day. Substance C represents high-value targets, mainly glucose. It gets filtered out initially, but the kidney spends a ton of energy completely reabsorbing it back into the blood because obviously you don't want to just pee out your valuable energy sources. Finally, substance D represents certain drugs and compounds like PAH. These are not only filtered, but the kidney actually goes out of its way to actively secrete more of them straight from the blood into the urine to aggressively clear them from your system. Section 5, eGFR and kidney health. Okay, this brings us to the climax of today's explainer. How do we take all this incredible microscopic physiology and use it to protect your health in the real world? To measure your overall kidney function, we need to calculate your GFR. In a perfect, purely scientific laboratory, we'd use a substance called inulin. It's a plant starch that undergoes pure filtration, no reabsorption, no secretion. It gives us a perfect GFR reading of about 125 milliliters per minute. But to test this, you'd have to sit in a hospital connected to an IV drip for hours, constantly monitoring your urine. That's just not happening for a routine checkup. So in the real world, clinics use creatinine instead. It's a natural waste product from your muscle breakdown that's already floating around in your blood, and conveniently, it also undergoes almost purely filtration. By checking your creatinine levels, doctors only need one simple blood draw to estimate how efficiently your biological filtration plant is running. And that estimation is exactly what the eGFR is. It literally stands for Estimated Glomerular Filtration Rate. Using your routine blood test for creatinine, alongside a few variables like your age and sex, healthcare providers run an equation to give you a highly accurate score. Historically, they used an equation called the MDRD, but today that's largely been superseded by a more accurate model known as CKD-EPI. The single calculated number is vastly simpler than asking you to collect all of your urine in a jug for 24 hours, and it's an incredibly powerful tool used to spot chronic kidney disease long before you'd ever feel any symptoms.
Now, what's really interesting about this visual is how clearly these numbers anchor to real human outcomes. If your eGFR is reading between 90 and 120, your internal filtration plant is operating optimally. Everything is great. But as that number dips between 60 and 90, we start seeing early-stage kidney disease. The filter is slowing down. Between 15 and 60 is established kidney disease, where toxins might actually start to build up. And if that number crashes to between 0 and 15, that represents critical kidney failure. At that point, the biological filter has essentially stopped working, and medical interventions like dialysis become completely necessary to do the job the kidneys can no longer manage.
We've seen exactly how incredible the glomerular filter is, the precise physics driving it, and the brilliant ways we can measure its efficiency. Because the kidney is just so phenomenally resilient, it often suffers in absolute silence when things start to go wrong. So if measuring your eGFR can spot a decline before you even feel a single symptom, when was the last time you checked your numbers? Next time you get a routine metabolic panel, look for that eGFR line. You'll now know exactly the microscopic marvel it represents. Thanks for joining me on this explainer, and keep learning.